Thank you to the organizers for giving me the opportunity to speak at this very interesting meeting. So what I really wanted to talk about in general was the wave equation, because that's somehow the topic of the meeting, I guess. For, I would say, somewhat more generally, this is, as I said, what I wanted to talk about, not what I will talk about. So the wave equation for interesting metrics. So what I mean by interesting metrics, well, of course, they're the metrics, sort of metrics I've been studying and trying to understand for a little while. So the first one is the Weil-Petersson metric, Weil-Petersson metric. So this is on Riemann moduli spaces. So there are several Riemann moduli spaces. The second lecture is, oh, you laugh. On, let's say, the L2 metric for on magnetic monopole spaces, again, there are several of these. The third one maybe is the one that's almost easiest to talk about, is the Hilbert scheme, planar Hilbert scheme for C2. And so this has Joyce-Nakajima metrics, and more generally, one would want to do quiver varieties. And finally, it would be interesting to talk about the metric on T star of GC. This is due to Kronheimer. So as I say, these are, fortunately, the organizers have only allowed me to speak for 1 hour, and so I'll talk about the Weil-Petersson metric. So these are interesting. I could spend the time just explaining these metrics. So these are rather natural metrics. The Weil-Petersson metric we understand very well. It's been studied, for a long time, and now we understand it quite well. The magnetic monopole metric is fully conjectured. The structure of this is conjectured completely, but not fully understood yet. The Hilbert scheme, the metric here, is now completely understood in some sense, asymptotically. This, we don't really have a conjecture yet. So this is the complex cotangent bundle of the complexification of a compact Lie group. So in these three cases, I think I'm going to lose my microphone. So these three cases are hyperkähler metrics. And in all cases, it would be very interesting, first to understand the Laplacian and ultimately to understand the wave equation. So they're all very interesting. In these three cases, complete hyperkähler metrics. So they're slightly less suitable perhaps for this meeting because what one would be studying is in some sense scattering theory for these metrics. Now, this one, on the other hand, is an incomplete metric, also Kähler, but I think it's very safe to say it's an extremely interesting metric, so I want to try and explain the structure of the Weil-Petersson metric, and then make some mostly conjectures about the behavior of the wave equation on it. Okay, so first of all, let me sort of start with trying to understand trying to write down the Weil-Petersson metric. So let me just do it locally first. So suppose we're interested in a manifold which will have corners in some sense. So let's say we're in codimension k corner. This is a local description of Weil-Petersson. So in here there are positive variables, so we're close to a codimension k corner, and then there's a manifold. If we want to think this globally near a k-dimensional corner, then this will actually be itself a compact manifold with corners, probably, depending on the size of k. And so try and write down some iterative structure for the Weil-Petersson metric. It looks, roughly speaking, like this. So these are just single normal variables. Sorry, I missed a factor. I'm pretty far gone here. So let's say that's a little better. In these variables, so what we're talking about here is actually a Hermitian metric. It's actually a Kähler metric. Let me hide the Kähler structure for the moment and say what this looks like is rather like the metric on the cusp of on the complete near the end of a cusp in a Riemann surface, and in fact, so actually it might be better to say it inductively. Let me just say it inductively here. So this, if you like, is just 1. So this is a cusp metric. It's not, what we have here is not a cusp metric, but it has an additional factor. There's some constants here which we won't worry about. So this is the normal direction as we go down to t equals 0, t1 equals 0. There's essentially a cusp, except it's scaled by a factor of t. And then, so this is codimension k. I'm sort of writing things down iteratively. So then we have a metric on the rest. So if you like, I'm separating one factor of this out, and then the rest is locally a manifold with corners. And so this is supposed to be an inductive definition. So here we have a metric, and then there's plus error terms, which we have to be careful to specify precisely, and so I won't for the moment. But so this term is inductively the same. On 0 epsilon to the k minus 1. Okay, and so there are, when we approach a corner, codimension k corner, there are essentially k of these factors, sum of these terms, plus a tangential term. And so this is actually, if you like, another Weil-Petersson metric, plus these quadratic terms. So this is how the thing behaves inductively. So I should have said this, as I'll explain in a minute, is joint work with Xuwen Zhu. Okay, now, so what I want to do is I want to talk about these metrics a little bit, talk about the Laplacian and so forth. But I thought it would be a good idea to explain where this comes from. So this is Weil-Petersson metric, and so I need to explain a little bit about, whoops, so I've already failed. Okay. So I need to explain a little bit about the Riemann moduli space and where this metric comes from. So I don't want to make this too heavy, but let's face it, the best way to do it is algebraic geometry, but fortunately I'm not an algebraic geometer, but I did have to read this stuff, and so I can at least report a little bit about what this is from an algebraic geometric point of view. There are also other points of view. So let's just start off with algebraic geometry here. So consider a fiber map. So here we're in a complex setting. So these are holomorphic manifolds, and a holomorphic map between them. Now, and so let me make some assumptions about this map, which is to say it's the simplest sort of thing. One is that the map is a holomorphic, so complex holomorphic, I'll say that is sort of given. Phi star is surjective. So we're in the context of a fibration in some sense. Secondly, we'll assume that the dimension of the fibers of the inverse image of a point in M is equal to 1. So this is the complex dimension. So the complex dimension of a fiber is 1, so we assume some other reasonable things, which are the fibers, which are these things, are compact. And let me just add things that you would assume anyway. So let's... Okay, so this is a complex fibration. And so the implicit function theorem applies. Of course, it's a holomorphic map, therefore it's smooth in the usual sense. The differential is the complex differential, but that's the same as the other differential. So the fact that it's surjective means the implicit function theorem, or whatever it is, applies. The fibers are smooth. Because of 3, they're compact. So the fibers are 2 real dimensional spaces. They're 1 complex dimensional spaces. They carry a complex structure because they're sitting inside C with a complex structure. So this is the natural notion of a fibration in the complex setting. So the trouble with the complex setting is that the global part of the implicit function theorem doesn't apply. So it is true that all these fibers are diffeomorphic. So these fibers, all of the fibers are diffeomorphic to a fixed Riemann surface. This is just the implicit function theorem. So as a smooth map, this is locally trivial. If I take an small open ball here, the inverse image is a product with a compact fiber. But what happens in the complex case, of course, is that the complex version of the implicit function theorem doesn't apply. In other words, this thing is not complex trivial near the fibers. It's not a product. And exactly what this is describing is the variation of the complex structure on the Riemann surface. So that's what's varying, really, the complex structure. The Riemann surface, in some sense, well, I mean, depending on what you think the Riemann surface is, as a real manifold, it's not changing. Okay, so this, if you like, is the simplest sort of classification theorem, and it has only been studied for what, 150 years, I suppose. And so Riemann already suggested what you can try and do as an algebraic geometer, as I say, which I'm not, but what you can try and do as an algebraic geometer is construct a global classifying version of the same thing. So this is supposed to be a classifying version of the same object. It's a moduli space. So what this is supposed to be is the same properties here, but it's supposed to have the property that as soon as you have one of these, then you have a map, a holomorphic map here, and a holomorphic map here, which is fiber preserving. So this, which is just to say this diagram commutes, meaning the fibers here are mapped to the fibers there, and this holomorphic map is supposed to exist, so this commutes. And this is the universality of the moduli space. In other words, any one of these things looks like, you can say, the pullback of this one. So locally, this thing is obtained by this, by mapping this into here. Of course, this map need not be an isomorphism or anything like that. For example, this could in fact be a constant family, in which case this would be the constant map. But the question is, does this always exist? So the claim is this exists and unique eta. This is the moduli space condition. Now, so this is the Riemann, so this is the Riemann moduli space. And this is the universal curve over it. Curve, because it's one complex dimension. So in other words, you're supposed to think of the points in here as actually classifying the complex structures on this manifold. All complex structures occur, all complex structures occur exactly once, they occur holomorphically, and so you can construct. So the idea is this exists is not, of course, obvious, and I'm not going to try and construct it. Now, you can construct it in various ways. The algebraic geometers constructed this a long time ago. You can also construct it fairly directly, differentially, geometrically. It's not that hard, although. So there's nice accounts of this which I can relate to anyone. So there are certain problems, namely, this doesn't quite work. Okay, so there's some problems. None of them, I would say, serious from our point of view. So first of all, it's certainly not always true. We need stability. So the moduli space doesn't exist. So the problem is, the main problem here is the existence of holomorphic self-maps of the fiber. If there are holomorphic self-maps of the fiber, it causes trouble, and stability is the condition that there should be no family of holomorphic maps. And so this can be expressed in the following way, that the genus, which is 0, 1, and higher, should be bigger than 1, which I write in that rather strange-looking way. 2G is bigger than 2 just means the genus is bigger than 1. So in other words, you're not allowed to have either spheres or a torus here. Okay, so that's one problem. There's an additional problem, which is that even when you exclude, so this stops the families of holomorphic self-maps from existing. So there is a SL2R on the sphere, and there's a single group on the torus, and this stops these occurring. There's another problem which you might think of as sporadic self-maps. So because of this, you have to take some little local quotients. That means there's no problem here, but this thing is not actually a manifold, it's an orbifold. It just has, but you should not lose a moment's sleep over this. It doesn't matter at all, except that it makes annoying problems when you try and write things down. So it's an orbifold. There's an additional problem that would frighten you even more, which is that it's not even a manifold in a categorical sense, it's a stack. Now this is a very minor detail, because this doesn't actually occur here. So I'll say in a minute why this occurs. This is not something worth worrying about at all. Okay, so so this is like too easy. We want to make the thing a little harder. And so the way it's traditionally done to make it harder is you think of n sections of this. So these are what are called pointed Riemann surfaces. So all you're doing is you're taking n points distinct in each fiber and allowing them to vary holomorphically. So these are holomorphic sections, but they're distinct holomorphic sections. And so then, of course, you need to do the same thing here. And then the stability condition explains why I did this before. That's the stability condition. So now G is allowed to be 0, provided n is at least 3, and G is allowed to be 1, provided n is at least 1. And that still kills the group, because now you're demanding that the holomorphic transformations on a fiber leave these points fixed. And so exist. So anyway, so the stack is, this is really G equals 1, n equals 1. And if you remember your Riemann surface theory, these are these are the tori with a marked point, torus with a marked point, and as a result, it's a group, and there's a self-map which is inversion. So there's just one self-map always. These things are sporadic. These are just isolated Riemann surface. This is, everything has a self-map, and because of that, you have to keep track of the maps. This you shouldn't, again, worry about in the slightest. So this is just, in this case, it's a stack, but that just doesn't mean much. Okay, so this exists, and it's been studied for a long time. So what is the, so in some sense here we have divisors. That is, we have n sections of this bundle over here. So you can think of these as n hypersurfaces inside this space. And so one of the things you want to try and understand, one wants to try and understand this. Of course, we understand a lot about it. I didn't say what the complex dimension is. But this exists and is pretty well behaved. Now, a long time ago, it was understood that this carries a canonical metric. And that's what I want to talk about. That's the Weil-Petersson metric. Now, of course, we all know that the fibers of this and the fibers of this also carry canonical metrics. Namely, this is a Riemann surface with n points removed. You should think of those points as cusps. So there's a unique, because of the stability, there's a unique metric of constant curvature -1, which is finite area outside those mark points where it has cusps. And the cusp is exactly like the metric that I wrote down a minute ago. So this has a family of metrics on it, and they're well behaved. I mean, of course, they're metrics, they can't be holomorphic, but they're real analytic in the base variable, so they depend, if you like, analytically on everything. Okay, now, so these are unique, so these are invariant under holomorphic self-maps and so forth. Now, so where does the metric come from here? Well, one needs to understand a little bit about the structure of the Riemann surface. So just one very nice way of understanding where this metric comes from is an idea of Robin and Salomon, I think. But in any case, it's older in a certain sense. So this space here has to have the property that there are really no constant the complex structure is really moving from point to point. And this has to be true even infinitesimally. Otherwise, it doesn't work. And so if you think about the fact that the curvature has to, the complex structure has to change on the fiber as the point in the base moves, you can have an idea of what the cotangent bundle, so it's usually explained in terms of the tangent bundle, but what the complex cotangent bundle of this space, which is more correctly, by the way, written that way. So this is Gn. So this is genus G, if I didn't make that clear. So the first question, so this is a complex manifold, as I said, and so you're interested in the holomorphic cotangent bundle. And so, not totally surprisingly, this can be realized as an object up here. So what it looks like is this. So this is sort of the basic Riemann surface theory. This is the space of holomorphic sections of the corresponding bundle on the fibers. So if I put a point here, on the fibers squared. So these are holomorphic, so-called holomorphic quadratic differentials. So this is a complex line bundle, a holomorphic line bundle over the Riemann surface. It's just the cotangent bundle squared. It's a line bundle, so you can square it. And these are the holomorphic sections of that. If we add these markings, these are allowed to have with simple poles at the marked points. So this is really some version of Riemann rock plus stability if you look into it. So you can think of this, I was going to explain it, but I don't, I'm obviously being very slow, that this is like an index theorem on the manifold where you're computing this space in some sense as the index. So this is a canonical identification of the cotangent bundle of the base, where we can put a metric. I mean, you would normally put it on the tangent bundle, but we can put it on the cotangent bundle. And this is a space of holomorphic sections of a bundle on the fiber above a given point. So it's fairly clear, I think, fairly simple. Now, only one board moves at a time, okay. So what does this buy one? Well, if we think about a tangent vector here, a cotangent vector, T1, maybe two cotangent vectors, because we want to get a metric, what we have to do is somehow pair those to get a metric. Now, what we have over here, I mean, this is an isomorphism, canonical isomorphism. We have corresponding quadratic differentials here. So these are just the images of those up there. So these are multiples of dz squared on the Riemann surface with a coefficient which is allowed to have poles at the specified points. And obviously, if you think about it for a minute, you'll see that raises the dimension by n when you add the n, allow the n poles. Okay, so what do these things look like? Well, as I say, Q1, so this is obviously what we're interested in if we want to have a Hermitian metric. So what does this look like? Well, it looks like some coefficient which we have to think about, locally, and what we get is dz squared, dz bar squared. Well, you can think of that as dz bar squared. Okay, and so this is the square of an area form. And so you might hope to integrate it, but you know you can't integrate the square of an area form. We know you can integrate an area form, but we have a metric on the fiber, so we can add, this is the area form for the metric. So this is the hyperbolic metric in the standard sense on the fiber at a given point. So we can just divide by that. So what does this look like? Well, near a pole, it looks like something like this. Near, we actually know more or less what it looks like. That's what it looks like near a cusp. Anywhere else, it's just a smooth, positive form. Now, if you do a little bit, so this, of course, means that cancels off with that, and you have an area form. So now you can see what the Weil-Petersson metric is the integral of that. So I think it was Petersson who realized that this was integrable. So even though we have poles here, we have this factor, and so if you look into it, you'll see that it's still integrable near a pole, because this thing is the standard area form. The worst thing is these could have simple poles, which is the same as this. The log here, it comes out the front, but it's still integrable. Log squared is integrable at the origin in R2. Log mod z squared. So this exists and is a well-defined metric and very heavily studied metric. Okay, so what's the question? Well, it's a Kähler metric. There's all sorts of things that are known about it, and I'll try and say a few of those in a minute. The question we want to ask is, can we do function theory? So I didn't say, but going back here, there's a problem if we want to try and do analysis. So the problem is that this is non-compact. This is a non-compact space. And so if we speed a little bit forward, I guess we're actually into the second half of the 20th century now. The compactification of this was sort of a rather remarkable. Maybe I'll just cheat by using the same diagram here. So this was a badge. So let me remove these hats. So this is the universal case here. Now, so what happens if we try to compactify things? Well, it's sort of mysterious, but the algebraic geometers have mysterious ways. And so what they realized, this is Deline Mumford, and actually Knudsen in the case of n positive, So what they realized is that if you replace this, these are fibrations, if you replace these by minimally degenerate fibrations, then you can ask the same question and get a compact space. So this is the Deligne-Mumford compactification, and these are now complex, compact manifolds, except for the same problems with orbifolds and things like that, which you shouldn't worry about for a moment. So what does this mean? Well, all we have to do is change this. Well, of course, you then have to do a whole lot of work to construct the space. But the question is just to change this to 1 prime. So what we want to say is near each point up here, so now we're generalizing this from fibration to a slightly more general class of maps. Near each point up here, we have either phi star is surjective. So the complex implicit function theorem does work locally. So if this is a surjection, it means there are holomorphic coordinates here which pull back the holomorphic coordinates there when you add a bunch more. It's just a projection. Locally, nothing happens. Locally, the complex structure is doing nothing. The variation in the complex structure is global on the Riemann surface, not local. Nothing happens locally. Or it looks like this, or it's Levschetz, which is to say it looks like this. So we have some variables in the base, Z2, Z3, however many variables there are. So this is in C, near a point in C, and then they're mapped to Z2, Z3. So this is the fibration. So there's always one, I mean, the fiber has dimension 1, so at a regular point, this is just, there's an extra Z1 here and then an extra free variable. At the singular points, what we allow is 2 extra variables, Z and W, and then here's 1 extra variable. So this is 1 extra variable in the fiber as opposed to the base, which is what it's supposed to be, and T is equal to ZW. So anyone who knows what I've been doing for the last 30 years will understand why I was attracted to this. This is also the minimally degenerate, of course these are complex variables, but these are also the minimally degenerate variables in a complex structure. So I'm being very slow here, but let me just say, what does this mean? So what does this additional property mean? So then you just run through the same theory. Then this thing exists, this exists, it's universal for these maps, it has the same properties. You have to think about stability. So we have to add a condition, I mean, we have to improve this stability. So this is an additional assumption here, the stability. I have to say what happens at the degeneration. But there's a similar condition at the degeneration. So what does this mean? Well, locally, it looks like this. So from the complex analytic point of view, of course, and so if we think of mod Z, mod W equals mod T, and then just think of the circles going around in the other directions, we see that we have a thing that looks like, it's really more like the positive quadrant multiplied by the circles. But so in the limits, what the fiber looks like is this Riemann surface, which has a self-intersection, which is called a node in algebraic geometry. So this is really what's happening. What we think secretly is happening, and indeed it is that the Riemann surface has a little geodesic, which is shrinking to have 0 length. That's what happens as we approach this point where this. So these are automatically isolated. There can only be a finite number of them over a compact set. This is what we think of in the real context of a geodesic shrinking. You think of this somehow as doing a singular thing, but in the complex setting it does not. It just is a Riemann surface which has suddenly a self-intersection. And it's completely transversal, nothing bad happens there, except this point is a double point in the Riemann surface. So the Riemann surface has just linked itself backwards from here. Okay, so it really, if you say it, of course, you have to think of a Riemann surface as being a little more complicated than this. And so you're shrinking some short geodesic. If you shrink several, and you can shrink several of them simultaneously, but they're always far apart. So what can happen is the thing can break up into smaller genus Riemann surfaces. But amongst the things that are not allowed to happen is that this is not allowed to happen anywhere near these points. Okay, so this is not obvious, I think, it's fair to say, that this exists, but that's what the literature tells us. And so I'm not going to try and beat that into you. Took a lot of beating into me, I can tell you. Okay, so from this point of view, the analytic question becomes, so now what we've got, if we have M, G, N bar, all this has is a bunch of divisors meeting transversally. So there can be quite a few, depending on the genus, and N, there can be a lot of divisors, but this is all that's happening. So within this, we just have what's like the complex version of a manifold with corners, a bunch of normally intersecting hypersurfaces. This is all that can happen. It's, again, not quite obvious why that's the case, but it's true. So this is in the parameter space. In the Riemann surface, you can have this more complicated behavior. Okay, so the question is, here we have the Weil-Petersson metric, because this is the regular part. What the algebraic geometers have done is add these normally self-intersecting divisors to compactify the space. That's what they've achieved. So we have the Riemann surface. That means so the regular Riemann surfaces are here, but then as we approach this surface, some geodesic shrinks to have zero length as we approach this, and another one somewhere else does. At the intersection, two do simultaneously, but they're far apart, and so nothing much happens, except things do happen. But okay, so the question is, how does GWP behave near the divisors in M, G, N bar? Okay, so it's perhaps time I give you at least I mean, this is history, but of course it's potted history. So a lot is known about this, and so this is the answer here. So what we're doing, these TIs are the TIs are 1 over the log of 1 over mod Zi. So that's also the variable that one introduces near a cone in the standard Riemann surface. And this theta I, so if you like, Zi is equal to mod Zi e to the I theta I. So these theta i's are just the arguments of the complex variable defining a divisor, and these are the distance from the divisor but turned into a 1 over log, so stretched out in log. And so then this is the answer to what the metric does. And so this has a lot of remarkable properties, and that's really what I wanted to point out. Things that one would just be embarrassed to say analytically, to assume analytically, because first of all, this, when you restrict to a divisor, what you get is another Weil-Petersson metric on the divisor. So one of the things that happens here, it's not that hard to understand, is that the divisors consist of not quite products of moduli spaces for the Riemann surface into which the thing is broken down. Not quite products because there's a finite you have to take a finite cover, because there's an issue about whether you know which point is which, and that. So, but this is the Weil-Petersson metric for the divisor. And so there's an error term which is pretty small, so I haven't explained what the forms are, but let's just accept for the moment that it's distinctly smaller than these terms. So this is really a decent expansion. Okay, and so amongst the other things that happen, the things that happen is that in some sense this is totally geodesic. I mean, this is a very, very close to a product metric. And there's additional things that I didn't explain. One of the most important ones is that, so if we're working in local coordinates here, we can say this is extremely small. So this metric is almost totally rotationally invariant. Of course, there's this, but the coefficients don't depend on theta. So again, you would be embarrassed to assume this in a standard setting, but it's true here, so, well, we can live with it because it makes life a lot simpler. Okay, so let's just have a, so this, I should have, so this, they're the main people. So Maser, around about 75 or something, Howard Maser, this is, showed that the metric was quasi-isometric to this. Weil-Petersson proved at some point in between that it had this, where this error term was just basically little o of 1. Abitsu and Weil-Petersson got a formula like this, but where this error term, however, was just in some C1 space. So what I'm asserting here is that the coefficients are smooth. Smooth, well, they're not quite smooth, unfortunately, but they're smooth in a way that we can live with, that again is another thing that you shouldn't concern yourself with. There can be logs in the expansions, that's all. But they're not at the top. Logs somewhere down in the expansion. So this doesn't matter. So they're basically smooth functions of the TIs, and the variables here, the tangential variables. So this is the lower, some lower Riemann moduli space. Okay, so what's known about this? So as I say, a lot was already known. Let's see, okay. So the first question is, so I've still got 20 minutes. That's the first minute of my first 10 minutes of my first talk. Okay, relatively recently, so of course you can write down the Laplacian. I won't insult you by writing down the Laplacian. Obviously, it's got some rather singular terms if you think about it. And so one of the things is it may be nicer to, if you feel a little more comfortable doing this, it may be nicer to introduce the square root of Ti, because this you can put this way. One factor of Ti like that, just absorbing the factor in the front. And then if you introduce S is Ti to the half, this becomes ds squared plus, you've made this rather simple, plus this, however, is made rather worse. And of course the coefficients are still smooth. They're in some sense even now in S. So in terms of this, you can rather easily guess what's going on. So this makes it look almost like a flat, like a flat Euclidean metric where we have corners. So this, remember, is iterative because this thing has again such an expansion. So there's an order Si to the fourth now, has such an expansion in terms of each variable. So all I'm saying is when we come to the boundary in one direction, this is what happened when we go up to the boundary, but of course this, when you go to the boundary, has another term like this, and so on. So really there's a sum of terms like this if you write it down. Okay, so this is essentially self-adjoint. So in other words, if you just take the domain to be compactly supported functions, smooth functions away from the divisors, then there's a unique self-adjoint extension. This was shown by G. Mazzeo, Muller, and Andrasch. Well, they only did it in the case n equals 0, and they didn't use the full strength of this, so they had to work rather hard. Once you've got this, it's rather obvious that the Weil-Petersson, that this Laplacian is essentially self-adjoint. Why, you might ask? Because as I say, it looks very much like a complete, a standard incomplete metric. In fact, the thing looks extremely like a product as you approach the corners. There are unfortunately these lower order terms which stop it being exactly a product. And there's this term. So this term does two things. One is it introduces a term that looks like this. in the Laplacian, which is a bit disturbing. But we know that singularities are good, not bad, in operators like this. On the other hand, it also does something otherwise you would sort of think it was something like the ordinary Laplacian, but that's not quite true, because this also changes the volume form. And changing the volume form changes the solution. So formal solutions, so if we had the usual elliptic boundary problem, then the formal solutions would be, the constant and the linear function, Dirichlet and Neumann conditions, and you have to specify which one you have to choose. Here the formal solutions are 1, corresponding to the Dirichlet problem, and s to the minus, s to the minus 4. Is that right? T to the minus 2, I think that's right. Okay. So this is not in L2 with respect to the metric. You're going to easily compute. And so this is why it's essentially self-adjoint. You don't need a boundary condition here because there's only one legal behavior at the boundary. Of course, you're asking about corners and so forth, so I don't say this is trivial by any means, but it's not very hard to prove essential self-adjointness. As I say, these guys did it with one hand tied behind their back because they didn't know the regularity of the metric. But once you know the regularity of the metric, it's a bit easier. Okay, so we can at least start to ask questions. So not only that, but again, these guys also show the resolvent is compact. So rather remarkably, we're sort of in the smooth manifold case. It looks rather like a smooth compact manifold. And so this is really what I was trying to say in these lectures, that we should try and understand these funny-looking metrics, which are very natural. They don't quite look like the metrics that we usually study. And so we should get on with it and do it, is what I say. Perhaps you should get on with it and do it. That's the trouble. So let me try and list some, since it's getting rather late, let me try and list some claims and conjectures. Oop, that's the wrong one. It is a bit slow. Okay, so I'll try and list claims, conjectures, and questions. Claims means that I believe I know how to prove them. Conjectures means I think they're true, and questions means I'm not sure whether they're true at all. So first of all, we can rather easily do. So I should have added that this, the function theory for this Laplacian was more or less done by Jesse and Jan Swoboda. So in fact, Jesse is precisely the reason why I started to use pluses between authors' names, because otherwise he was getting too much credit. He was both Gell and Redman. Okay, so they worked in the lowest. I mean, it's easy to go back. So in the cases where g is equal to 0, n is equal to 3, g is equal to 1, n equals 1, then there's only one divisor, and this translates to a true boundary problem. It's still not trivial to solve, but this was done, well, the heat kernel was really done by these two guys. Now, in fact, we believe that we can do the whole thing. So what does the whole thing mean? Well, one thing you would like to prove, so the claim really, well, let me put as a conjecture here. This is really a claim. So for an example would be the held L2 harmonic forms are equal to the actual cohomology of the compactified space. So this is again something you wouldn't normally expect. So this is of course the de Broglie cohomology, or the rational cohomology of the space. So the Hodge theorem is perfect on this space. Even though things are weird, it behaves like a compact manifold. So this is like the general question. So what I'm really supposed to be talking about here is the wave equation. So let me at least try and say some things. Of course, we're talking about just the wave equation on functions. We'll do, this is on forms. So what can one expect to be true for the wave equation? Well, of course, in the interior, we all know what happens. And so it's only a question of what happens near these boundary faces. And so, well, first question is geodesics. Well, this has, again, been widely studied. Let me explain in a minute what was known before. So without this smooth structure, it's a bit much harder to understand geodesics. But first of all, it is incomplete. So the metric is incomplete. That's rather obvious that you can just get to the boundary in a finite time. But if you get to the boundary, the only way you can get to the boundary in a finite time, if you think about it, is the dual variable to the theta variable has to be very, very small, has to vanish. You have to be stationary in the theta variable. So what happens to the geodesics is sort of interesting. For some reason, I haven't seen this picture in the literature. So you have a geodesic. There are geodesics. So this is the divisor. So one of the divisors. There are geodesics that come straight in and hit the boundary. They don't have to be straight. I mean, they don't have to be normal. But most of the geodesics turn around very rapidly. So this divisor represents an enormous barrier. Almost all the geodesics are bang. So if we think about the dual variable to theta I being some kappa I, this is really essentially at kappa I equals 0. It's not quite because the metric is not a product, but it's at kappa I equals 0 to infinite order. So most of the geodesics go back, and indeed, it's known, this is a paper not that long ago, Burns, same Maser, and Amy Wilkinson, show that the geodesic flow is ergodic. But so this geodesic flow is not well defined. The set of rays that can reach the boundary has measure 0. It's easy to see. So it's essentially, you know, for those guys, it's good enough for the ergodic people. So not only is it ergodic, but it's actually Bernoulli, if you know the difference, which is to say it's even better than ergodic. So it's extremely mixing. It's mixing to all orders. Now, with this form of the metric, so this is, I think it was Woolpert actually who observed these things were measure 0. And so the metric, the flow is mostly defined off a set of measure 0. And ergodicities, as I say, this is a paper only about, I don't know, 2011 or something. Not that old. Now, so in fact, if one wants to understand the wave equation, of course, we know we really want to understand geodesics a bit better than measure 0. So let me just sort of indicate what, you know, whoops. Oh, this is the middle one. What I do, because I've been doing it for a long time. So in the interior, for geodesics, we have the sphere bundle over the interior. So this interior, so remember there are a bunch of these divisors. M0 is the interior, Mi, and then this thing is M1, 2. So there are the intersections of the divisors, multiple intersections. So this is the unit sphere bundle or cosphere bundle, let's say. So this is where geodesic flow normally takes place. And indeed, it does take place here, but this is the open manifold, and so we have to take count of this. This is fine, but we have to add something about that. So we need to put in the, we can do it this way. We can put in the ball bundles on the MI. So this is the unit ball bundle, co-ball bundle, cross the corresponding circle. So that's not right, is it? Yeah, so that's the MI. So I'm using the complex notation here. So this MI is the complex hypersurface. It's where Zi vanishes. So it's got codimension 2, not codimension 1. So in other words, the circle variable is killed in here, and the dual variable to the circle variable is killed. And so this is just keeping the circle, corresponding circle. So we have a bunch of these. And then you need to continue to do it for the balls for the Mij cross Si cross Sj, and you need to go exhaust all of the strata of this thing. So this is a stratified manifold. It can have things up to codimension, I forget what, some function of G. Okay, so if you look at this space here, which is a CW space, so this is some sort of CW space. It's a lot nicer than that, because what it consists of, so I have to tell you how to glue these together, but these, of course, are glued in at a corresponding place at the boundary, which you can guess if you look at it. The geodesic flow makes global sense on this space. So what's happening is that, again, I said it's a miraculous, but when we pass to the boundary, there are geodesics in the boundary, and there's a natural reflected flow. So the geodesic flow makes sense on this in exactly the same sense as it occurs on boundary problems. When you hit the boundary here, you go into the interior of this, and you reflect back. I won't write the formulae down, but exactly the same as usual reflection. The angle, when you arrive here, this has to be constant, and so there's a circle of directions that you can arrive in. The boundary of this is the unit sphere. These are the points that are actually inside the surface and stay in there. It's totally geodesic. When you do geodesics in the surface, it stays in there. And so, of course, when you go to the boundary of this, you have to do this again. And in some sense, you're going from this, and so you get these higher ball bundles. And so you might ask, well, what happens to the solutions of the wave equation? Since I have got very little time left, let me at least say a few things about what I expect for solutions of the wave equation. So first of all, how bad are things? Well, you've got to remember this is a miraculous thing here. Whoops. I think I need to get my driver's license here. Okay. Can you see that? So it's a miraculous thing. So you know, hope for the best, and it's likely to be true. First of all, the wave equation is well posed on the energy space. That's nothing. That's just because it's a self-adjoint operator. You just have to work out the energy domain, which is easy enough to write down. So the wave group exists. This wave group exists in the usual sense on RT cross the actual, I mean, it's on the energy space in the manifold. And so you might ask, well, what do solutions actually look like? So if you even forget the finite energy condition, but look for solutions, so of course you want this equation to be non-singular, so you just look for solutions on RT cross M0, the open part, where it really makes sense. So you need to demand that these are tempered as you approach the divisors. So it just means Schwartz. They can blow up to polynomial degree. Demand that. Then this actually implies, so this is, if you like, partial hypoellipticity in this context, that if you smooth them in time, so this depends on the time and the space variable, I write it as m, if you take the convolution with a test function in time, so this is the time convolution, phi is just any test function, just what you'd do on a usual compact manifold. So in the compact case, this is smooth. In this case, it's essentially smooth. So you just have to remember, so this is really the manifold, the whole manifold, but we have to allow just logarithmic singularities. There are logarithmic singularities everywhere here. they're in the coefficients, and so there's no getting rid of them. But this just means that in the expansion, there can be powers of log, but these are just growing linearly with the powers, so it's not serious. And in particular, the leading term has to have no logs, so actually the restriction of U to all the boundary faces, this exists as a distribution. And so this again is rather miraculous, because as opposed to any problem that you've ever seen before, this satisfies the induced wave equation on the corresponding hyperspace. I mean, it's somehow bizarre. So this actually satisfies the wave equation on the interior of this. Remember, these are iteratively the same sort of space. And so this is true to all orders. It satisfies the wave equation. And so it's not, so I will just say very briefly, what can we expect? So claim there is a wavefront set on this, well, it's not quite that space, but let me just pretend it's that space. Yeah, actually, it is that, that'll do. On that space, capturing singularities for solutions, not for arbitrary distributions, modulo this. So if the wavefront set is empty, you've got a smooth in time and space solution. So there's a notion, and this and Hernandez's theorem holds. Almost holds. Okay. Well, Jared will tell you where the fly in the ointment is. These corners are corners. Even though they're very square, there are lower order terms. And so what I'm saying here is that the singularities are traveling along these rays, which just look like this, but when it goes to the corner, there is a unique reflection for a ray going into the corner. Let me draw it like this. There is a natural reflection because it's smooth to high order, it's a square to high order. But nevertheless, the diffractive front will come out at a lower order. So substantially down. So this holds, so this is modulo lower order. So the regularity of the diffractive front, so this is claim, probably the last part is slightly conjectural, but I think that's pretty clear. So Hernandez's theorem holds, modulo some additional stuff, diffraction coming out of the corners, but rather minor detail. So this implies Weil estimate holds. So if you want to prove this yourself, go ahead, because I'm not going to do it. But it's pretty clear that Ivry's proof of Weil asymptotics. So this is asymptotic actually with the standard remainder. So I should have said, of course, from this theorem you get a Doistermaat-Guillemin theorem about the location of the singularities, and they're isolated at 0, you can easily see, and so the Ivry's argument for Weil asymptotics hold. You get the usual asymptotics, the area, the volume of the manifold is finite, you get usual Weil asymptotics. Here is a question, is there a 1 over log improvement? After all, this is an extremely nice manifold, and so the curvature is negative, the sectional curvatures are negative in the interior. They are not uniformly negative, they're not pinched above and below. As you approach the boundaries, some of the curvatures go to 0, but in a very clear way. So it's possible that this is true. Also, I would say because of, so I've run out of time, but I was going to give a whole list. Maybe I'll write up the conjectures, but quantum ergodicity. Does quantum ergodicity hold? It's certainly perfectly reasonable to expect. Maybe, I don't think it's quite reasonable to expect unique quantum ergodicity because there are these boundary terms, but who knows? Maybe one can say something rather precise about that. I don't know, not my department. This pretty clearly should follow from standard arguments if you have the properties of the waveguide. So there are many other such questions that we could ask. Well, or really I'm saying is that once we get a setting like this Weil-Petersson metric that somehow just is so much above what one would expect in the way of good behavior that we should study it and we should see what happens. The same is true for lectures 2, 3, and 4. I'll stop.